Yep, that's good. Okay, so couple quick reminders. Wednesday you have some exercises due. As always, feel free to hang out after class if you have any questions. I'll also leave some time at the end of class on Wednesday. My goal is to leave some time on class Wednesdays to get anything clarified. And hopefully you've already started the project. You may have ran into a couple little hiccups that might need help solving, so I'll give you some tips on working with floating points today. There's multiple solutions to it, so I'll kind of go over something that doesn't require importing other people's code, which is what happens when you have to use the word import. So if you've Googled anything and you see something where it says like import decimal, basically you're importing other people's code that kind of already dealt with problems. My intention was really for you to not use that. If you used it, ultimately I didn't put any restriction in the specifications, so if you did, that's fine, but I would encourage you to consider how to do it, which is primitives, which I'm going to kind of allude to a little bit today. Okay, so again, I want to mention a few things from last class where we ended. Remember we did like type of 3.14, and 3.14, what type is that? It's a float, and again, we used the type method to figure that out. So what we're going to talk about, it'll probably still be 3-4 weeks away when we actually start writing our own classes. So you can see it says class float. So classes have attached to them something known as methods. A method is like a function that belongs to a class. So the way you access a method is just to go ahead and, I'm just putting in parentheses, to emphasize like, here, let me do it like this. Let's just call this f equal to 3.14, so you can see that I went ahead and actually stored the float in f. So if I do f and then dot is the syntax to access the methods of a class. And as I mentioned at the last time, f dot is integer, will return true or false, and it will basically it'll just check if there's any sort of significant decimal. So if we did like f equal to 3.0, while f is still a float, because its decimal is just 0, if you were to do f dot is integer, it will go ahead and return true. So again, that's something that you can do to make sure that a user inputs some sort of valid change amount, but you will need to do a little bit of computation in terms of kind of multiplication and things like that. So that's what we're going to talk a little bit more. We're going to go ahead and just write a little program that illustrates issues with floating points when it comes to programming languages. And then let's also, because again, this is a course called Mathematical Computing, let's go ahead and understand the underlying mathematics, why this is an issue. So to illustrate the issue, let's go ahead and just declare a variable. Let's go ahead and actually make it a float. So let's declare x to be 0.0. And let's go ahead and increment that by some float. So let's go ahead and define another variable inc for increment as 0.01. So basically, we're going to go ahead and count by 0.01. And let's go ahead and count to 1 by tenths, which we have right here. So the way we do that is we'll just go ahead and say for I in range of 10. Because remember, that's going to basically go through a loop 10 times. And each time we're going to add to x some increment, which is 0.01. And just to kind of see what happens, let's go ahead and print x. And let's go ahead and run this just so we can see kind of what is happening. So as we could run this, you could even kind of already see there's some really strange behavior right here. And we're going to kind of explore that a little bit more. But one thing I'll go ahead and note, I'm sure as you learn more about programming in Python, you're going to Google things just to kind of figure it out. Notice how all of the logic within this block did not rely on the variable we're incrementing, I. So there is something you might see. If you just put an underscore, this is like a throwaway symbol, like, hey, I just need to loop 10 times. I don't care to store that value anywhere. So if you see that, you can go ahead and that's what it means. It's basically the logic does not rely on some incrementing variable. I just want to do something 10 times. I'm not going to do that just because it's something, honestly, I didn't learn until like after I'd been programming Python for a while. So just if you see it, that's a little FYI. So again, I'm going to just, I is going to go through 10 times. I'm not going to use I because I'm just incrementing X. But again, just to see, like, I could go ahead and print I, and I could say, I'll just say something like I is, just so you see what's incrementing, a little bit of a review. You can see I is starting up here. I is 0, I is 1, I is 2, I is 3, I is 4. I'm talking about myself a lot today, so let's just delete that. So again, just wanted to kind of let you know about that. So you can see even what's going on right here. There's some weird stuff happening, like with this, like I was not expecting 0.799999999. I was expecting 0.8. So what's going to happen as you start trying to do some comparisons with floats, it might be natural to say something like, let's just say if x equal to 1.0, so if we've this is what we're expecting. If we went ahead and added 0.1 to itself 10 times, we expect x to be equal to 0.1. We'll go ahead and print that f, so an f string x equal to 1.0. So if you have equality, it will go ahead and do that. Else, I will go ahead and just print this, just something that say x is not 1.0. So just a kind of a quick little review of branching. And I don't necessarily need to print x each time. You kind of already saw this. But if we run this, what branch do you expect to occur? The if branch or the else branch? Say again? Oh, I thought I heard it. Maybe that was just Dr. Guy. So you logically you expected the if branch to run, but in reality the else branch did. So we're going to talk about why that is occurring from a mathematical sense. But before we do that, let me give you a couple ways that you could go ahead and deal with that. Suppose that you do need to work with floats in your program. There's really two ways that you can go ahead and deal with this. The first thing that you can do is kind of a calculus kind of idea. It throws out the letter epsilon. So what we could go ahead and do to deal with that is instead of testing for some equality, we can test for a lack of error. So what we'll do up here at the beginning, let's go ahead and also declare another variable called epsilon for error, which for those of you who have taken Calc 1, which is a prerequisite for this course. So let's make it a very small epsilon. So let's let the error or epsilon be approximately 1/100th. And then what we could do instead of testing for equality, let's go ahead and change this right here. We can test that the 1.0 minus x is less than some error. But of course, remember, if you remember like delta epsilon proofs from calculus, it's not just the difference, it's the absolute value of the difference. So again, that just makes sure you don't have to worry about magnitude or direction. So to take the absolute value of an expression, you can just go ahead and type ABS or abs around it. So I'm going to also just say is almost 1.0 because technically there's something going on when it comes to the solving or to the incrementing. It's not quite there in the bits in the computer, but for our intents and purpose and our logic, you can see now the condition the if branch ran and not the else branch. So this is one way to deal with floating points. This is especially good if you need to keep precision, because you can see this one's saying, I'm going to keep precision to 100th place. Again, if you need more precision, you can go ahead and increase your epsilon. By the way, I think it was, I saw this a few years ago. I have to find the article again. It was, here, let me see, NASA number of digits of pi. You would think like NASA would need to use a lot of like precision when it comes to their computations, but NASA only really needs to round 15 digits of pi for all of their computations that are like in the universe. Like we only need 15 digits of pi. So if you have 15 digits of pi memorized, like hey, you're better. More than that, you're better than NASA. Anyway, I thought that was interesting because you would think something as big as the universe would need more than 15 digits, but you know, God must have known what he was doing. It's like fine, they're imperfect. They only need 15 digits. They'll be able to get around with that. Anyway, thought that was interesting. So this is one way to deal with it. Any questions? Another way to deal with it, and this is something that I used a lot last summer in the course I was taking. I took a game artificial intelligence course, and if you think about it, everything we do in life is really continuous. Like motion is continuous, but it's hard to go ahead and hold on to something that is changing like infinitely many times. And again, this is getting into ideas of calculus and things like that. But there's a process known as discretization. So let me go ahead and so we can go just so you see. So to discretize something means that we're going to take something that's continuous and basically approximate it using something that's discrete, so integers or discrete. So another way we can go ahead and solve this problem would be as follows, and this is kind of the approach that I used when I was working on the project that I assigned, but again, there's multiple approaches. So what I'm going to go ahead and do is I'm going to kind of keep this same setup, but I'm not going to use this epsilon. So I'm going to go back to where I was before. I'm going to go back to this logic. Where was it? So right here. I'm not going to use the epsilon. I want to go ahead and use a process known as discretization. So this will also give us an opportunity to go ahead and introduce a few more tools. We're really getting a lot of tools in our tool belt that we can really start now getting a lot of problems. So what I'm going to do is introduce another variable that's a Boolean. I'm going to go ahead and do a Boolean that says is discretized. The reason I'm going to do this is because I really only need to do this to float. So like if x were not a float, then I wouldn't need to go ahead and discretize it. But this kind of illustrates a program paradigm known as basically this is a flag. So this is something like if I do something at the beginning, I may need to undo it at the end. So this is just kind of a programming paradigm. I'm using a flag variable. If I do something at the beginning and I need to undo it at the end. So what I'm going to go ahead and do is I'm going to go ahead and discretize to 2 place values. So if this is going to be I only need to worry about this if I'm incrementing, I guess, by a float. So and there's a new function I'm going to introduce right here, is instance. What is instance is it has 2 arguments. It's going to take a variable, so increment. If that variable is an instance of some class, and it is a float, go ahead and do something. So is instance will either return true or false. And it will return true in this case because the increment variable is an instance of a float variable type, or class, I should say. All right, so if we're working with a float, what I want to go ahead and do is say, okay, I'm going to discretize this. So I'm going to set that to true. So I'm doing this. And what I'm going to do is I'm going to set x, and I am going to go ahead and multiply it by 100 and cast it to an integer. So if you think about it now, if you just kind of think about the logic, let's run it through. Print x now. X is now, I'll say it this way. X is now, just so you see it, x. So let's run that. And you can see right here, x is now 10. We've multiplied it by 100. 0.1 by 100 is going to give you 10. So, so that is the discretization process. But what I'm now going to do is I'm going to increment the 10 times. And since I discretized this at the end, what I'm going to need to do is if I did the discretization process, so after I loop, so if is discretized, so if true or false, and in this case it's true, what I need to go ahead and do is divide x back by 100. If we run this, let's see what we have right here. This is so you can see right here. We still run into this right here. How did I deal with that right now? Hold on, let me think. I forgot. I dealt with this the other. So if x is, I was explaining that. Okay, I think. Hold on, give me 1 sec. Oh, this still does. That should have worked. Anyway, I guess oh, maybe it was this. Let me also do round to 1 sec. Oh, because I think I have to also discretize the incrementing count. So then I also need inc to be integer because I want to go ahead and work with, I think that'll, yeah. And yeah, that was right. Sorry about that. I forgot something. So x is equal to x divided by 100. Okay, yeah. So let's fix that. All right, so let me back up a little bit. So we multiplied by 100, and basically, like I said, in the discretization process, we're going to go ahead and work with integers. So I also need to go ahead and cast this to an integer, which means I have to also, something looks off, hold on. X, hold on. Sorry about this. I've lost my logic here. So if discretized is true, what I need to do is I need to multiply x by 100. I also need to go ahead and multiply, oh, I think this is it. Hold on. Because I was expecting that to be true. There, got it. Okay, sorry about that. So if we're going to discretize, we need to discretize x by multiplying it by 100 and casting it to an int. In the same way, we have to discretize our incrementing variable by multiplying 100, and then we'll go ahead and cast that to an int. We go ahead and do the incrementing, and if we had discretized, we're going to go ahead and reconvert that to a float using standard division. And now that basically avoided all of the issues that come with the issues with the floating points. So, yeah, come on.
Like a number is not
Let me. So her code still looks the same, and it's one of those things that this is, I guess I use this as an example just to show discretization. I really would recommend, though, that you would use that epsilon method. I think there's still something going on under the hood that this doesn't completely solve all the time. And I'd have to look at Python's implementation about that a little bit more. But let's go ahead and talk about mathematically, why does this happen when we're not discretizing. So if I were to just comment this out, if I were to not, and like, why does this weird rounding thing happen? Okay, to figure that out, what we're going to do is do something a little bit more mathy than programming-y. So let's go ahead and let's just think about our numbers for a sec. So if we were to go ahead and consider the 302, this is a decimal number. We work with the base 10 system, so we could write this as 3 times 100 plus 0 times 10 plus 2 times 1. Does everyone agree? That's the expanded form. So how many numbers can we represent with 3 digits? We can represent 0 through 999, right? So in other words, 3 digits can represent 10 to the 3 values. But computers, they use binary. And again, you guys did some binary back in discrete last semester, right? Okay. So binary, what is the base there? Does anyone know? 2. Hopefully the bi gives it away. So binary base 2 are basically zeros and ones are the numerals, are the digits we have access to. And by the way, when it comes to programming, these are typically referred to as bits. So these, and a 0 means off or false, and 1 means true or on. So again, a computer is basically just flipping bits really fast. So just to make sure we're comfortable with different bases, let's just maybe review that. And I think you guys did this last semester in discrete, but it's up at still place value. So if you did 1011 base 2, what is the decimal equivalent to this binary number? Well, you would just look at you would basically just go by powers of 2. So this first one is in the fourth place from the right. So this is going to be 1 times 2 to the 3rd because we start at 0, plus 0 times 2 to the squared, plus 1 times 2 to the 1, plus 1 times 2 to the 0. So this is just going to be 8 plus 0 plus 4. Wait, hold on. Yeah, 8 plus, oh, that should be 2. 2 plus 1, or is 11. Everyone see how I got that decimal value? Okay, so just to make sure, let me give you a moment. 11011 base 2, what would that be? Let me give you a little moment to think through this. Once you think you've got it, turn to your neighbor and tell them, hey, I think it is, and answer it. Hey, Alejandro. Anyone think they got it? Let me give another sec. I see those pencils flying. Kenneth is like, I got this in my head. Do you?
No, I got it wrong.
Oh, no. All right. Anna, you think you know it? Do you and Kenneth match? Caroline, Lois, did you two get it? What'd you get? It is 27. Yes, the answer is 27. By the way, I took a computer architecture course, non-degree seeking, and boy, we dealt with this a lot. I always find it easy just to start from there and do 1 plus 2, then I skip, so that's 4, then this is 8, and then this is 16, so it is ultimately going to be 27. So instead of doing the expanded notation, binary is actually a really nice base system to work with because it's really just summing powers of 2, and when there's a 0, you just skip that power. Okay, so these of course are integers. So Again, our issues are coming when it comes to floats. So what about decimals or floats? So decimals or floats. Well, what we can do is kind of that same idea with powers. Is we can use a tuple. Tuple is an ordered pair, and what we could have in the first is an integer, and then we could have some power in the second one. So for example, for a decimal or a float, what we can do is 1949, and we'll do -3. So we have some integer, but then a power. So this would end up being 1949 times the base right here. So what we can now do is represent some decimal using two integers, just a pair. So we have then the kind of the implication that we're going to work with some base. So this, of course, is decimal. So this is a decimal example. What about a binary example? So let's do a nice one first. What if I wanted to represent 6 to 5? By the way, this is the fraction 5/8. So how would I represent this as an ordered pair? Well, if we think about what we've encountered so far, we need the 5. So the 5 is going to be right here. And then we're also going to need let's think about this. If we're doing binary, 8 is 2 to the what? 3. So this is 2 to the third. So we're going to take the 5 right here, and we're going to take the 3 right here. But this is still not quite right, because those are still decimal representations. So what we want to do is consider 5 and binary. Anyone know what 5 is really quick? It's 4 plus 1, so 101. And then we're going to have to do 3, or a -3. So we would have a minus, anyone know? 1. So this right here is how you could go ahead and represent. Now this is ignoring the fact that we still haven't talked about representing negatives. And there's actually 3 ways to do that. There's either signed magnitude, 1's complement, or 2's complement. We won't go into that in this course, but all have their pros and cons. So this right here is how we would represent this float with a pair of integers. Let me give you one. Let's try another example. What about 7 over 32? How would you represent this fraction using a tuple? So, let's make that a little bigger for you. Anyone think they know? If you do, ask your neighbor if they know and see if you agree. Your neighbor may be in front or behind you, in the case of the right side of the room. Yeah, Caroline?
Why are both of the second
Why are both of the second numbers
numbers negative?
negative? Say again?
Like in each of the examples, we have like 3 that's negative and it's also negative.
Yeah, so we're thinking about how can we represent floats. In order to do a float, we're going to need some integer, and then we're going to need some power to create that decimal. So remember that whenever you have a negative exponent, it just divides. So that's why we can go ahead and we're doing 1949 divided by 1,000. Yes.
Okay.
So again, so we were like, how do we represent that number? And I just kind of did the reverse here. Let's start with this. How do I represent this using integers? Okay, bless you. So anyone think they know this one? Maybe. What do you think, Andrea? So it's going to be 111 and
And then negative 100 something.
a little too far. 30, wait, maybe you were right. Yeah, say that again, 100.
100,000.
32, yes. So hold on, I have to visualize this. So 32 is not, oh wait, not quite. 32 is 2 to the what? To the fifth. So how would you do, it's the exponent that goes here. So 5 is going to be 101. So to recap, the numerator is right here. So this is 7 in binary. And then 32 is our fraction. So to get 32, I'm just going to go ahead and use the exponent because it is a decimal number I'm looking at. So this is how a computer could represent this decimal. Is everyone okay with that? So far everything's playing out pretty nice, right? Lois, Alejandro, do you have a question? Can I help with something? Okay, just wanted to make sure. So this is what, so far everything's nice. So what about though, so what if we were to do 0.1 or 1/10? How would I represent this like I did above? Well, here, does anyone see what the issue is? Just glancing at that fraction. It's not a power of 2. So 10 is not a power of 2. So what do you deal with? So again, or how do you deal with this? So this is not a power of 2. So what you need to do is you need to get close. And what we can do is do like 3 over 32, which is 0.09375. So this is really close to what we want, but it's not exactly. So that is where those little errors show up when you come with dealing with floats. That's because a computer is working with bits, powers of 2, but we're asking it to kind of represent something that's a power of 10. So, and of course, we can go ahead and do this in a similar way, that you can go ahead and do 3, which is 1, 1. So 0, 0, 0, 0, 1, 1, 1, and, well, actually, that's not even much. I wanted to say something about the number of digits here in a moment. So 0, 1, 1 is 3, and 32 is the same above, so negative 0, 1. So this number required 3 digits. Of course, you can get more precision. I can't remember, I think the Guttag book said if you let it go to 5 digits, you can go ahead and do something like 30 over something around 512 or something like that, so it gets more precision. Python uses about 57 bits to represent it. So Python uses 57 bits. So again, its precision's pretty close, but again, it's still not perfect. So that's why floating point errors occur. So it's something you need to be careful of, especially if you ever do like, let's see, floating point catastrophes. Let's see if these come up. Disasters according to rounding error. So let's see, you can see there are some pretty big deals for people who did not account for rounding errors. So this Ariane 5 was a rocket that exploded in 1996 because they did not account for rounding errors. Basically, it rounded up and it overcorrected and it blew up. So anyway, that's a fun little tidbit of computer science about rounding. Does anyone have any questions? Yeah, Andrea. Yeah.
On your line 11, I typed in the same thing, but it's throwing me a syntax error.
I'll have to look at it. Save it and we'll check it on after class. All right. Yeah, Ken.
So if we can fix the rounding error using all these like weird discretization and whatnot, then why doesn't the computer just do it automatically?
It depends on. So why doesn't the computer do it automatically? Well, if you were to, let me think about this question. That's a great question. So the question was, why doesn't the computer automatically just fix it? It is a design decision, to be honest. I'm not sure about it, the design decision of why the writers of the Python programming language decided to leave it there. It might be for something a little bit more underlying that I'm not familiar with about the language, but it's a design decision. They could, and I think like if you use the decimal class, that goes ahead and fixes it by defining a new class that does solve it for you. Some of it's also backwards compatibility. So if they want old code to work, they just kind of leave things a certain way. So this is an interesting question. I don't know the historical idea from Python why they chose to just kind of leave that as an issue. Might be an optimization thing because it is compiled down to a C language, but they may talk. You probably could Google it and find some information, but not sure off the top of my head. All right. So any questions on this? All right. So the other thing that I want to go ahead and look at today is something known as bisection search. So this is another mathy thing. So let's go back to the code. If you want to save this, you could probably just copy it over. What did we call this? Discretize.py. I'll just copy this over to another file. Hold on, let me get myself some space. Discretize.py. Copy that over, clean that. All right. And, all right. So a little bit of review from last time. Find the square root of a perfect square using exhaustive enumeration. All right, so this is by the way, what we're about to do is not how your calculator finds square roots. So I just wanted to illustrate this is what we're going to do is a type of guess and check algorithm, because I want to set us up for something later in this semester known as asymptotic analysis. So let's ask the user for an int. So int input. And I'm going to just do a very simple prompt of just something like that. And I'm going to go ahead and declare a variable just for illustration purposes called numGuesses. That's going to start at 0. And I'm going to go ahead and start guessing at 0. It's called guess and check algorithm, so we should have a guess. And I want to go ahead and track how many guesses this approach takes. So what we're going to do is increment guess until it is at least the value being checked. So while guess squared is less than x, what we're going to do is increment our guess count, and guess will be incremented by 1 as well. So we're basically going to try to find a perfect square by starting at 1 and squaring it, starting at 2 and squaring it, and so on. And we're going to check if it's a perfect square. So 1 squared, 2 squared. So this will basically, just to see kind of what our guesses are, let's just go ahead and print guess squared. So you can see when we run this, let's say, let's do a larger number. So let's do 1,000. Num guess is not defined because I need to spell correctly. So let's do that. So 1,000. So you can see it's checking all of these perfect squares until it gets over the value of x. So let's go ahead and I'm going to just comment that out so we can continue. So now what we're going to do is check if the input is a perfect square. So to do that, if the guess squared is not equal to x, we can just go ahead and print that the value of x that we're checking is not a perfect square. So we can go ahead and just do that. So we're just looking up until we've exceeded it or equaled it, because if it equals, again, it'll stop. So this is the case where our guess is not a perfect square. But the other case is print, we'll say it like this, I'll use an F string, the square root of x is guess. So yeah, sure, let's get that all up. Does that help? So go ahead and run that, play with a few different values and just make sure you're understanding kind of the logic. So you may run it. Let's type in 25. It says 25 is not a perfect square. Well, that's strange. Let's see. 25 is a perfect square. Why is that happening? Num guess is greater than. So guesses. So there's a bug. Let's track it down. So if I did 35, it's not a perfect square, but I was expecting this to print the square root of 25 is guess. So just to figure out what's going on, here's a little, let's go ahead and just run the debugger and let's kind of walk through this. So I'm going to run through it. And oh, I have to go ahead and stop the code, and then let's go ahead and run through it. Oh, so it's going to ask for input, let's say 25. So you can see what's happening. We have our guess at 0. Num guess is 0, and then x is the number we're checking. And why did that happen? That was weird. Let's try that again. So let's go to the next step. So num guesses went 1. So let's see what happened. So now our guess 1 squared, so that's still going to go in there. So num guesses is now 2. We're incrementing this, so you now see guess is 2, so we square that. It's going to be 4. It's still in there because that evaluated to true. And guess is now 3. I should have done 9. It is what it is. So now guess is now 4, and we're going to see next. Okay, so you can see right here, our guess is 5. We're going to square this, and this should evaluate to false, right? So in this so let's see what happens. That's what I was expecting. So if, oh wait, so if we look at this, guess squared is not equal to guess, then we print it as not a perfect square. So this logic is a little bit off because obviously guess squared is not going to be equal to guess, right? And honestly, some of you probably spotted that before me and just like, Mr. Tessler, what are you writing? But it just goes to show how easy it is to make a little bit of a typo. So what should this line be? And notice how I got stuck and I just started stepping through this one line at a time. It's going to happen to everyone. Hopefully it doesn't happen to you in front of a class, but you can see it happens. But I've understood this is the line that's wrong. Does anyone know what this line should be? Huh? Guess squared, and it should be not equal to, it needs to be the number we're checking, x. So here's my bug, because in this case we want this to happen because guess squared is our x. So let's go ahead and stop this and see this. Now if guess squared is not equal to x, then run this. But if it is, what we'll go ahead and do is go to the else. So there we go. I found my bug. So that took a little longer than I wanted to because I typed a bug. Does that make sense? So one thing I want to go ahead, let me just show you and we'll kind of explore it next time. Let's say just print something like this. That took num of guesses. So let's look at how long that took. So if I run this, so let's do 20. Hold on, num of guesses. Print f string. What are you saying?
There's an extra bracket.
Oh, I see. Thank you. Thanks, Andrea. So always read those bugs or those syntax errors. So now let's run it. Let's do 25. And I still can't spell correctly. So let's see. What line is that on? 19. Num, not none. Sorry, a little too holy there. By the way, if you guys have autocomplete on, that probably saves you from a lot of these little typos. So let's do 25. Okay. Oh, finally. Third time's the charm. Took 5 guesses. But what if we were doing a number like that? So a much larger number. I just went across the keyboard and did all of our digits. That took 35,137 guesses. Took a little while, right? So what I want to go ahead and do in this last minute is illustrate the idea of bisection search, and show you how much more efficient it is. And then next time we'll go ahead and code it up and go through the reasoning. So the idea behind bisection search is as follows. So let me show a little illustration over here. If you think about what we're doing, we are just guessing the square root and checking if it was the right number. So how many of you, when you look up a word in the dictionary, start at page 1 and flip it 1 page at a time? Anyone? I guess you just really want to know your dictionary. I'll see you in a few years because I'm going to ask you to look up the word zebra. What is a zebra? So I'll see you later. No, that's not how we look up words in a dictionary. How do you do it? If I were to ask you to look up the word, let's say, monopoly, what would you do? You would go to the M, but how would you do that? You would start in the middle, and if you were at you would kind of open it. If you were at O, what side would you look? Would you look at your left hand or your right hand? If you were at O and you were looking for monopoly, you would look at what hand? The left. You would want to go to the smaller value. So a faster way to find something, assuming it is sorted, is to start in the middle. And if you're thinking about a square root, you're typically going to want to look down to the left. So you're going to look down to the left, and you're going to update. Your original guess is now the highest point, and then you're going to go ahead and find the new middle. So you start with the smallest, the highest, and somewhere in the middle. And then what you're going to do, if you're too high, you're going to update your high, and then you're going to go ahead and find the new middle. And then you would just repeat that process until you found the correct value. So just to see how much more efficient bisection search is compared to that guess and check search, let me just go ahead and just show you, or just copy and paste the code in and pray that there's no bugs, because we've been a little buggy today. Sorry about that. But let's just go ahead and see. So can someone remember 35,137 guesses? So hold on to that. Let's go ahead and try a bisection search. And that was just all the numbers. Bisection search only took 51 guesses. So it is much faster. It's compared to a guess and check algorithm. And just to kind of start to introduce you to some words that we'll look at more later in the semester, the guess and check algorithm At worst case, it was a linear runtime, because if at worst case you have to check every single value, where the bisection search is a logarithmic runtime, where basically each step you divide the problem in half. So it's a much faster. So if someone asks you to find a word in the dictionary, I highly recommend a bisection search instead of just a guess and check, one problem at a time. So anyway, we'll kind of code this up a little bit next time to make sure we understand the intricacies of it. But does anyone have any questions as we wrap up the day? Okay. Good job today, everyone. Let me stop the recording, and if you have any questions, feel free to stick around. Otherwise, I will see you all on Wednesday.